So I changed my earphone. So can you hear my voice right now?
Yes, Sensei, can hear you.
Okay, thank you very much.
Most welcome.
So before you cannot hear my voice, right?
Yes, Sensei, I can't hear you while you were working.
Oh, okay. Oh, sorry, I don't know what's wrong, but maybe something maybe happened to my earphones. So I just talked a lot, but actually you didn't hear. Okay, let me explain again. So don't worry about that. So what I'm doing here, just copy paste the old segment 2 part to here, and I delete about structure part, and now I'm doing it again from starting. But we did use FFT. We import SciPy FFT here, but you can also use NPy FFT. Both are the same. Both are the same, right? And so this is the roughly summarize of what I told before. Okay, so let's continue. Let's continue. So I have some little problem. I think I'm recording right now, so don't worry about that. So I'm recording what I did, and let's see. So then FS is not defined. I think in wave input we already have FS. Return file. So why there are no result for FS? That's strange. So let me check. Print FS. Let me debug here. Autosave failed. Oh, maybe. Okay. Oh, okay. I cannot save this file. Oh, very strange. Let me try here again. You cannot run. Oh, okay. Something wrong with my kernel, so I will stop this kernel, and I will stop the page and do it from beginning. Okay. Sometimes bad things happened. So let me go back to assignment 4. I think everything is okay. A part of this are saved. Okay, part of this are saved, and but input. Oh, this part is not running. Oh, invalid. Okay, here we have a error here. When I'm doing the SciPy, no module named. Oh, okay. How about NPy? NPy. Oh, let me check. What other people do?
Yeah, so you have read the A50 two times.
Yes, I used twice because there is a package named FFT. So I think I just make some mistake on other part. Let me reference some page. You can also go to internet and search for these things. They can be easily found. Yeah, it is. It should be doing like this. Let me try using a different expression. I will use from and pi import FFT as FFT. It's better. Like this. Okay, how about this one? Dot FFT. How about this one? Okay, it seems work like this way. Okay, let me do this like this way. Okay, and I will use IFFT. No, here. The same package, right? But the different functions only. But thank you very much for reminding me my mistake. Please point out where I'm wrong all the time, so help me do the program better. Okay, so I have another arrow here. So right now I use the correct shape to import FFT here. But I have an arrow here because I use the round bracket. I should use square bracket here because it's the least in here. Okay, so same thing in here. I should revise this part. Okay. Okay, it seems it works. And let me plot. Let me plot the spectrum by F and by F. Okay. Okay, spectrum like this. You can see that most part are concentrating on this part, right? So I will like to focus on this part. So I will use X direction as a semi-log in X direction. So it will be, okay, it'll show like this, yeah, right? It's looked better, right? And also, I would like you to learn more about plot. So, for example, let's give them a limit, right? X lim. Let's say 0.1 to 10 hertz, right? So when the figure shows up, it will show only 0.1 to 10 hertz part. And I will give them a label as FFT, right? Sorry, it should be in the stream. And later, I will put a one comment in plot dot legend, right? And it will show a legend. I have it here. Also, I would like the legend font should be larger than this. So font size here, I think is roughly about 12, right? It'd be much better. So if I set them to 36, you can see it very clear, right? Maybe too much, 36 too much. It's 20, I think is good. And so you can change the font of everyone. So also you can change the X direction and Y direction, plot, X label as frequency, like hertz, right? And Y level like amplitude. So we're still using international unit. Oh, we didn't use international unit here. So in wave import, we will scale factor will be divided by 100. So I mark it change to unit from Gauss to meter per square second square, right? Oh, I didn't finish yet. So some misspelling. I think it's misspelling. So I have X and Y level, but the font is too small, right? So we can change the font here by just adding one variable here very freely. 12, I think, is too large, maybe 16. 16 will look better, right? You can see it very clearly in here with unit, right? Always with unit, please. And we can also change the shape of the figure. Uh, 606, I think. Oh, let me check. Wait a moment. Let plot figure size. I think it's just figure size. Oh, yeah, just figure size, right? Fig size. Right. So by doing this, we can. Oh, we show another figure. Let me try to do like this. It's better. Okay. So if you change to this one, then you can changing the ratio of the figure, right? You can see that it becomes longer and longer, right? You can change the shape of the figure. It's not working like I expected. Oh, not work very well. So okay, just ignore this part. So you can have the label and mark all in this figure, right? So I would like to make this as a function, right? Name the plot. Name define it as a plot spectrum. And with X and Y, and with label, and with X label and Y label, with F limit, Fs, Fe, something like this. So I'll change this to X and Y, and label equals to L, and oh, let me keeping this in memo here. Let me keeping this in memo here, and so this should be Fs, Fe, and this should be XL, so YL. So we can use this function to plot a spectrum. Instead of this one, we just put plot spectrum, use X is the F, Y is the F, and label is FFT, and XR, YR is the X label, and Y label is this one. This one, and this one, and Fs, Fy is 0.1, 10 seconds. So just delete this one, this part. Okay, so it should be, oh, it's wrong because we didn't run this part. So it showed up like we showed it before. Okay, so this is the first spectrum, it's a Fourier spectrum, right? And so we can know in each component, each frequency component is amplitude, we can know, right? So another part is to do this is a Fourier spectrum. Another small practice is to do a design or a spectrum, design spectrum. To design spectrum. So let's also do the function in the after the Fourier spectrum. Let's do design spectrum. Before we make a function, we just write it down here. So to give a design spectrum, we will give SA target, right? SA as an empty one. So we know a frequency, and we should find out the value for each of the frequency here. And okay, still we should make it to function. Define as design spectrum. Here we just use the example of using the we should have a range, right? A frequency start and a frequency end. And we'll use the Japanese design spectrum that we introduced in web class. Okay, where is it? So that's right, right? You can see it. It's just right here in the. Oh, this is a 7.3. Sorry, you see the 7.4. Sit in the 7.4. Here, so this is the equation for Japanese design spectrum in ground type 2, level 2, ground 1, right? Level 2, type 2, ground 1. Level 2 means very rare earthquake. So now rare earthquake in Japan is means very large earthquake, like the Kobe earthquake in 1995. Well, some of you even didn't born that time. Or the Great Japanese East Japan earthquake, 2011, also named as Toho earthquake, which caused the nuclear power plant accident in Fukushima. Very large earthquake. So type 2 means is plate. It's not. It's the directly under the fault is directly under the location of urban area. So it means that the source of the earthquake is very near to the construction location of your design target, and the magnitude is very large. It's magnitude 7, and the depth is very shallow, like 10 kilograms. So this is type 2 ground earthquake, very terrible earthquake. So you can see all the numbers are in unit of Gauss. So they defined by T, but so we need to change them to T in programming. So I will decide SA as empty, and or we can use n equals to length of f. Use 0. Sorry, np dot zeros of n, size of n, and we can use a for fi in f, for loop. So the ti will be 1 divided fi, right? Very easy. So we'll give them value if fi is smaller than fe and larger than, we can directly write like this, larger than fs. Then we will design the spectrum, right? Then we'll give them earthquake. So if, here we will practice our if function. If ti is smaller than 0.3, then we'll use this equation, 4463. Okay. So SAI equals 4463, and multiple TI. We use the power of 2 divided by 3. So your power in Python, we use 2 multiple squares, 2 divided 3, right? Power. And if it's larger than 3 but smaller than 7, we should else if. In Python, we use this else if like this. TI smaller than 0.7 because it already else, so it should be larger or equal. Let's see, also larger is equal, okay? Or small or equal. Then SAI, right, well, equals to 2000. Okay, it should be 2000, right? And smaller than, larger than 0.7 will be else. else. And else SAI will becomes this one. So SAI will becomes 1104 04 divide T divide divide T power of 5 divided by 3. 5 divided by 3. Okay, or we can just write multiple, but a minus 5 divided by 3, right? The same thing. Okay, so after that, don't forget to change our SAI to unit of meter square. Right? Say change unit from Gauss to, so I will then give SA. Oh, wait, we have problem here. A problem here. So let me set this is empty. So for each of them, SAI it becomes 0. So even this part they have value, others will be 0. So SA dot append SAI, and they will return SA. Okay, so let's try. Okay, other part I think we don't need then. Let me delete this part, and I will write SA equals to design spectrum, and so here let me use how to say that here FS is being used, so let me use FR here. This should be deleted. FS should be 0.1. So FE should be 10 Hz. So we will have a unified FS and FE here. So I use F and FS, FE to get the design spectrum. And I will plot the design spectrum. SA, this is design. Design spectrum. Okay, so firstly, I will read the function I read and then plot them again. Oh, something wrong. T is not, oh, some type missing. TI, zero. Counter double scala. I don't know what does that mean.
Sensei,
It's not good too. Yes, please.
The TI argument is wrong, partly wrong, something. Can you check it?
Which TI?
TI greater than or equal to 7, the upper limit, actually.
Upper one?
Upper one, upper limit, actually.
The upper limit. You mean this part?
Yes, sensei.
Oh. Should I change to this one?
No. Elif greater than or equal 7.
Equal 7.
Greater than. Sensei, can you check it? I think.
No. Yeah, when t is greater than 7, right? T should be greater than 7. However, this part is smaller than 0.3.
Yes, sensei.
So use else if, it means that it's larger than 0.3 and smaller than 0.7.
Yes, sensei.
See, so else part is should be larger and equal than 0.7.
Okay, sensei. Sorry for my.
So no problem. Okay, thank you for interactive interaction with me. So I think this part maybe only in the plot is the problem. This plot is the problem. Pound 3 runtime counter in double scalar. Oh, runtime counter in double scalar. So it's not this part. Oh, no problem. So, okay, so the runtime warning counted in double scalar. So what does that mean? Give me a warning. It should not be so much deadly problem. Oh, okay. Oh, I see. Because, okay. Because sometimes I find it's very small value, so I do this is in very dangerous way. So I will give them a very safety way to do this. One multiple 1e minus 32. Then it will be very large, right? So let me just using this part inside here, okay? So inside here. Then in this area is with safety. So there will be no way of TI in very wrong area. Let me try again. Still worrying about. Still worrying about this. Or maybe I didn't update this part. Okay, so the arrows goes away because I did something wrong in the okay, let me forget about spectral part. So make it shorter. Design, okay? So you can see the design spectrum is look like this one. Design spectrum is look like this one, right? So design spectrum, in fact, is a response spectrum. So a response spectrum can be calculated by the knowledge we learned before, right? So what we need to do is to do design spectrum. And to do this, we need change our Newmark beta method, okay? Before is MCK, but we need to change them to omega and H only. So here will becomes just following the equation we find, but we know that the C is 2H omega, so it's 0.5 HB becomes H omega, M will be omega square. Only changing is to do this one. So H omega 0.5 omega omega. C is 2 multiple H multiple omega omega multiple omega. Right? All in this are different. Okay, and this part also change this to 1. Okay. This is just omega square. Okay. So other part is the same. Other part is the same. Okay. So we need a function to define response spectrum for structure model, right? For earthquake with a dt and with a h and with a range, right? And which frequency, which which frequency we should calculate. And okay, so same thing, SA equals to empty list. And I will do a for loop for Fi in F. So I say I equals to 0. And if Fs larger than Fi smaller than Fe, then we'll do the calculation, right? So the Ti should be 1 divided Fi. Oh, actually, we don't need to calculate Ti. We just calculate omega will be fine here. Omega with Fi multiple 2 multiple pi. Pi is we use n pi dot pi will be fine. Okay, calculate pi. We already have H. So what I need to do is just call the Newman-Beta method to do this. Call this one. Okay. Oh, we need the beta. We need the beta also. We need the beta to decide what kind of calculation we use. We need the beta. So A V D is equals to this one. And then we will get we get AAD, then we can Z. Z should be let's make it to NP array. Or we cannot calculate it. A and NP array. So I cannot see the comment right now because the space is really limited. So you can, if you can interrupt me if you have find any mistaking I'm inputting. So please no hesitate to let me know. Okay, I'm very happy to you to talk to me because right now I'm very lonely because only one I'm talking. So I don't know. Are you already fall to asleep or something? So NP, this part is welcome to chat, no problem. And wave, minus this one. I hope you understand this part is to do the absolute acceleration by wave minus A. And in some lecture, the right side of AG is using minus AG, but here we use plus AG, so here is minus. So if we, function, this part is plus, we use minus here. If this is minus, we use plus here. Okay, so then we should know the maximum SAI should be the max of NP dot ABS, absolute value of that. So you get maximum of SAI here. And only if it works like this, okay? So, and then we will know SA dot append a SAI, and we'll return SA, just like other spectrum, right? Just like other spectrum. So we will code this spectrum and see what's wrong here, what is going on here. Okay, let me start another part. The SA is equals to this one. Because design spectrum is our target spectrum, so I use SAT here. And I don't want to calculate them again, so I just calculate that here indirectly here. I think beta we already defined here, okay, so no problem. Okay, error. The response spectrum is not defined. Okay, I need to run this part first and run this part later. Because this need a lot of calculation time. So please wait a second. I can't believe that there's no error. Oh, finished. So I need just plot them again. Plot them again. So this is not design, right? This is how to say response. To response. So I would like to do what I would like to do is not see them separately, but what I would like to do is to plot them together. So this is a response spectrum. So what I'd like to do is see them together. So I will make another function, just exactly like a plot spectrum, but I use plot spectrum 2. So there'll be spectrum 1 and spectrum 2. So L1 and L2, just like this. So I firstly plot spectrum 1 and then plot spectrum 2 with level 1 and level 2. So we can observe 2 spectrums together. Okay. X label, Y label. Okay. So I will try this function here. So SAT design and SA here. And the first one is design, another one is response. Other thing is the same. Here is just design 2. Okay, so let's see what's happening here. Oh, not defined. Okay, I'll update my function. Something wrong here. Okay, revise it. Okay, try this one. Oh, no, not this one. This one. Okay, let me delete this one to not make you confused, right? And you can see the blue one is the design spectrum. The orange one is the one we do for or response one, right? To make a design earthquake, we need to fit or design spectrum, make or response spectrum of the earthquake fit the design spectrum. For example, this component are larger than the design spectrum. So we will need to adjust or 1 second component, make it smaller so that can fit with design spectrum, right? So we should have a function to do this. Okay, let me show you how to do this. See code spec fit. So this kind of artificial design earthquake wave method is proposed by Professor Ozaki in University of Tokyo many years ago. So this method, anyone can generate any earthquake and ignore any physical issues of earthquake. For example, what is the source of the epicenter? What is source of the fault? What is the path of the propagation of the wave? All this information can be ignored. We just fit design spectrum by adjusting waveforms, okay, by their frequency domain component. So some of the physical scientists not agree with this method because it's a lack of scientific supporting of the physical meaning of this method. However, in design practice, we need this kind of design spectrum. And actually, this kind of all kind of earthquake waveform are possible to happen. So we need a lot of earthquake record. But however, in the real world, we don't have a lot of earthquake record. In Japan, we have a lot of record. But we cannot say that we all know about earthquake, right? There are still a lot of unknowns. So we should generate more earthquake to discuss or design. And for other countries, a lot of countries don't have seismometer like Japan. So we need to, but we have a spectrum, then we can fit spectrum by some artificial waves. So for engineer, this is very, very important method to do the system design for a lot of situations. So how to fit them? We need one small function to do the fitting part. Okay, firstly, define spectrum fit, and we need a wave, we need a DT, we need a F, and the FS and FE. We need SAT, target wave, and SA. And so we just writing and see what we need. So we just fit once about earthquake, right? Fit once about earthquake. So okay, we don't do the so we should so the length should be n should be length of should be the length of the f, right? We should, okay, we don't use, instead of wave, we use the fully transformed parameter y for this, okay? And then I use this one. For this for loop, I use I in range. In range of n. Range of n. So I will setting a scale factor equals 0 for every step. I will set the n equals to length of y. I will use another method as f is the change factor. After updating the spectrum, we call it f. So it will becomes use np dot. Okay, my daughter have some problem. Okay. And let's have a short break. I will stop the recording. Daughters and boys will interrupt or cause. Okay, sorry for the interruption, and so we'll continue with that. So I will make zeros. But here I need to make it zeros with Python. I think you should NPy. There's we need a complex number. So I will need the data type equals complex. Yeah, we need to this one. There's with a size of n and with the data types equals complex number. So other part will be 0 up here, and okay, let's see. Input is equals to x. Output like y. Output like y. So we scale factor equals 0, and we'll finally make a y. Y I equals to x I, but with scale factor. And don't forget the conjunction component. So J will be the conjunction component, which should be large N minus I, and my J is conjunction component should be conjunction of NP dot conjunction of y I. So the only problem is how to make the scale factor. Scale factor should be if f is smaller than fe, fs, this part scale factor have value, or other part it should become 0. So this should be s equals to SAT Right, so that's why we need I here. Too many of them need to be SA. So if we use this scale factor, then they will updating the spectrum for us, right? One by one. So we will return. Oh, but also we will calculate the or arrow here. We should calculate arrow here. And R should be MP dot zeros. And here is a real number, right? R equals 0. So the R is checking the relationship between this. Oh, this part should be I. R should checking the relationship between them, so it should be MP dot absolute value of 1 minus S. So because we're calculating the distance between them, okay. So, so here is not large n, small n. Sorry, small n. So I was setting R I equals to R. Okay. So after calculate that, we will calculate the arrow. Calculate arrow for all the components. So we'll see MP dot sum of R divided by is average value. So it should be divided by N. Okay. And so I will return later. Return 1 is Y, right? That's Y. And another is arrow in spectrum. So I need still we need a whole function means artificial wave, design wave. So we'll use a wave, a DT, as a target wave, and to do this, right? Well, okay, we just give them seed. It will calculate design wave by themselves. So inside this, we do a FS and FE part, and we will give them beta and H. What else? We set it here. Okay, and in here we should do almost everything we did here. We need to calculate the length of the wave. We need to calculate the length of the wave. And we need to do the Fourier transform to get the frequency of the things. I just copy paste this part to get the Y only. To get the Y only. Oh, got too long. Okay, so it's just like this, and I5T YX is like this, and I will get my F equals to E2 Q until to N. Okay. And so firstly, I will get SA. So SA should be SAT should get like this, and SA should be get like this. SA should get like this. Response spectrum and design spectrum. And later we will do a for loop here. Here we will learn a new one, okay? While loop. While loop was true. And when something we should times equals to 1, right? The first equals 0, okay? So here, inside here, times equals to 1 plus times. And we say if times is equals to t limit. We'll set a t limit. Limit times, right? For example, 10, right? For example, 10. Then it'll be finished. So we'll say break. And here we will call a function. Because we already did the Fourier function, we'll also spectrum fit. Spectrum fit. By this, we'll get a y and the arrow. So we'll give epsilon, which is small value. So if arrow is smaller than epsilon, then break. Okay, so after y, setting this y, we should give update or wave. So the wave should equals to IFFT y, but we'll take only the real part. And we'll calculate. We'll have to calculate the SA again, update SA again, until we see this. And what we output is to return or wave or SA, the arrow is what we need to do. Okay, so we already partly finished this program right now. So we just code SA and the wave, the SA and arrow equals to this one. We're setting limit equals to 1 and Fs equals to 0.05%. This means 5%. Oh, also, because when running, it will stopping for a very long time, so we don't like this. So we will, after calculate this, we'll have print something like runtime number dot d arrow equals 6.4 f. So in here we will percentage about times. Oh, maybe put times here. and arrow. So we can see what's happening here. Okay, so let's try to run this one and jumped this part, jump this part to this part. Maybe I think maybe the FSFE is too large. So let me just see equals 0.1, FE equals 0.2. Okay, so make it quicker. Okay, here's something wrong. When this step happens, true array more than one element. Okay, because it's it should be a vector in F. So we cannot use F like this. So we use F I. Okay. Another arrow here in this one, J. Index is outer boundary of 0. Okay. Because the first one we don't check the first one. So when it ranges from 0 to n minus 1, right? So if equals 0, so n minus 0 is 406. So we don't do this. So we just starting from this one. Okay. So we change the range from E1 from n to 1 to n. Okay, runtime arrow, this one. Okay, and finished. Now to finish that, we should plot the wave here again to see is that improved. Okay, to see it's improved or not, we need another plot. Means plot 3. Plot 3, right? 3 is y2 and y3 and label 3. Just to put one more line here. Okay, so I'll run this one and run this one. Okay, and so for here, yeah, this SA 2. Okay, so SA and SA 2. Design response and artificial. And so let's try this one. Okay, so seems to be fitted here in this one. Let's try a little bit more excited part. So this is a design one. So this is an original one. So this is an artificial one. So it seems this changed better. Let's make it to 0.1 to 1 second. Let's see what's happening here. May cost a little bit time. Okay, so you can see that after artificial adjusting, it changes better. And let me change. Oh, so it's 0.1. Sorry, to 10 seconds. Let's try a full course, right? A full course. Let's change a full course. What's happened here? It should be better than this one. It should be better than this one. it costs a little bit of time. Also, depending on your computer and the program you're writing. Okay, so we just run one time, and because time limit we set it as one time. So you can see after one time updating is obviously becoming better, right? So if you give the limit to more times, like 3 times, it's definitely going to change better. But I don't have time to show all of you here, but you can try it later by yourself and setting the epsilon even smaller and to let them fit it better. I think it would be to do the great work. Okay. So that is all for today's lecture. So I will stop the recording.